electro electrochemistry. Okay, so let's quickly go over some of the basics of the topics that I'm quite sure that you are aware of, right? So when you go ahead and you talk about it, when we talk about our electrolysis, so an electrolysis, what is electrolysis? Electrolysis is basically the decomposition of an ionic compound by the passage of electricity, by the passage of electrical current into its elements or into its ion, right? So if I take an ionic compound and I break it down into its elements with the help of an electrical current, that is going to be known as electrolysis. Now, when we talk about electrolysis, electrolysis is generally one of the most common uses of electrolysis is that we use it in extraction of highly reactive metals. And we have studied this before in our IGCSE as well, right? For example, aluminium. Aluminium, if you remember your reactivity series, so aluminium was above carbon in the reactivity series. Because of that reason, we could not use carbon, we could not use reduction with carbon to go ahead and actually extract aluminium. We could do that for iron, we could do that for copper, right? But we could not go and do that with our aluminium. So we had to go for electrolysis. So highly reactive metals that we have, they have to be extracted using electrolysis. Other metals, of course, we can simply heat them with carbon and we can extract them by using carbon. Another use for electrolysis was that we had studied was purification of metals, right? So if I want to purify copper, I can use the process of your electrolysis. And also certain non-metals like chlorine, they can also be purified by using our electrolysis. Along with that, we also this is the uses for electrolysis. We also use it for something known as electroplating. Electrolysis, if you remember, we used to do it by using the help of an electrolytic cell. We used to have our power supply. The power supply used to be connected to our electrodes. We used to have the cathode and the anode. The anode was the one that was connected to the positive terminal. The cathode was the one that was connected to the negative terminal. And it used to be surrounded by a solution of our ionic compound, which we used to call electrolytes. One thing that we have to remember about our ionic compound is that the ionic compound had to be either molten or in the form of a solution, because we don't want any because we need free ions, right? We need free ions to allow the conduction of electricity. So in solid ionic compounds, we don't have any free ions to allow the passage of electrical currents. So we have electrolytes, we have our cathode, we have our anode. So electrolyte is the compound that gets decomposed, right? Electrodes are rods. We can make them either from carbon or we make them from a non-reactive metal like platinum. And then we have, of course, our power supply. Now, when we talk about the reactions that take place in electrolysis, so on our cathode, the reaction that takes place is known as reduction. Reduction, as we remember, and I'm going over this quickly because we have studied all of this before. Reduction, as we go ahead and remember, is that reduction is the gain of electrons, right? So at cathode, we will have cations. Cations will be attracted to the cathode where they will gain electrons, right? So reduction, always what happens at the cathode reduction. Just letting you know, if you take electrolysis and if you take a cell, both of them come under the topic of electrochemistry. And cell, a fuel cell or a normal battery, a normal simple cell, and I take electrolysis. Both of them are under the heading of electrochemistry. In your topic of cell, you will see that the term anode and cathode are reversed. Anode we use for the negative and cathode we use for the positive. You might remember this from your IGCSE as well. But even though the terminologies were reversed, cathode was the positive electrode, but the reaction that was happening at the cathode was still reduction. Okay, so cathode is always going to have reduction. So wherever I'm seeing reduction, that particular is going to be known as my cathode. So then we have our anode. Anode is where our oxidation is going to take place, and oxidation is the loss of electrons. And if you remember, whenever we are making our half equations, how do we make our half equations? So we make our half equations like this. For example, I'm doing electrolysis of zinc chloride. So zinc will go to the cathode, where it will gain 2 electrons and it will become zinc metal. And on the anode, my chloride ion will lose electrons to become chlorine gas. But since we never write down electrons with a negative sign, we would write it on the other side of the equation, like this. So this is how we had studied in our IGCSE. This is how we were making our ionic equations. So this second reaction is the reaction at anode. And this is the reaction, the top one, at cathode. Again, I'm going over this fast because this is stuff you have already done in your O levels. But if any of this is something that you want me to repeat properly, do let me know. Okay. So this is basically what we had studied so far. Now, when we talk about our electrolysis, we can actually do certain calculations that will allow us to know what is the mass of substance that, for example, is deposited during electrolysis. For example, I'm doing electrolysis of zinc chloride. Again, zinc metal will get deposited on the cathode. So I can actually calculate how much of the zinc has been deposited on the cathode. Now, the mass of a substance, any mass of a substance, that is the mass of a substance that is produced during electrolysis is proportional to two things. One, the time over which the constant electrical current passes. So time for which constant electrical current passes. Secondly, the strength of the electrical current. These are the two things the mass of the substance will depend upon. So how much mass of substance we're getting at the cathode, for example, it will depend upon the time and on the strength of the electrical current. We can write it down as, so we know, if you have done physics, you would know there we have a formula. Charge is equals to current into time. This is the formula for charge, right? So charge is, we measure charge in coulombs. See, the unit for this is C. We have I. The I stands for current, which is measured in amperes. And then, of course, we have our time, which I'm sure you know that the time stands for seconds. So I can take my charge and I can calculate it by multiplying current with time. So the mass of substance produced at an electrode or the mass of substance removed from an electrode during electrolysis is proportional to the quantity of electricity. The quantity of electricity is measured as charge. 1 second. So it's going to be measured as charge, right? So our charge is proportional to the mass of substance that is going to be produced at an electrode or removed from an electrode. We can, another unit, right? The quantity of electricity that I'm talking about over here, the strength of the electrical current. This another unit we can use for this is Faraday. So if I want to calculate Q, I can also measure it with the unit known as Faraday, the symbol for which is F. So, and what is Faraday? Faraday is the quantity. 1 second, let me actually type it out. Faraday is the quantity of electrical charge. It's the quantity of electrical charge carried by 1 mole of electrons. Right? So, for example, if I have silver that is being deposited at the cathode, so it will undergo reduction and it will turn into silver metal. Over here, I have 1 mole of electrons. So the charge that is going to be carried by 1 mole of electron, that charge is going to be known as Faraday. And it has a fixed value. It has a value of 96,500 coulombs per mole. So this is the value for 1 Faraday. So if I want to form 1 mole of silver, I need 96,500 coulombs of energy, right? If I am depositing copper, so Cu2 plus 2E gives me copper metal. Over here, I am doing 2 moles of electron. So I will actually need to multiply my answer by 2. So if I want to calculate how much energy I need or how much electrical energy or how much electrical quantity I need to move 1 ion of copper or to deposit 1 molecule of 1 atom of copper, I will have to take 96,500 and multiply that by 2. So that actually gives me the answer of, oh wait, let me open up the calculator. 96,500 multiplied by 2, 193,000 coulombs per mole. This is the amount of energy, or just coulombs actually. This is the amount of energy, or this is the amount of charge. This is the amount of charge that I will need to deposit 1 atom of copper, right? I will either need 193,000 coulombs or 2 Faraday, right? 1 Faraday is for 1 mole. So the amount of energy I need for 2 moles is going to be 2 Faraday. So either you can give your answers 2 Faraday, or if you want to calculate in terms of coulombs, so 2 multiplied by 96,500, right? So this is how you're going to be able to do your calculations. Similarly, okay, what if my hydroxide ion goes to the electrode? So if hydroxide ion goes to the electrode, we get water, we get oxygen, and we get electrons. I will quickly balance 4 over here, 4 over here, and my oxygen is supposed to be 4 as well. So I put 2 over here, right? I'm getting 4 moles of electron. So if I want to calculate how much energy I need, so I will, sorry, I'm saying energy, how much charge I will need. So I will have to take 96,500 and I will have to multiply it by 4. So if I take my 96,500, if I take 1 Faraday and I multiply it by the mole of electrons, that will tell me how much charge I need to deposit or to remove 1 ion or 1 atom. Making sense so far? Any confusion about what we discussed so far?
No.
Okay. So we can use the value of F. We can use this value of F to calculate, one, I can use it to calculate the mass of substance that is happening at an electrode, and two, to calculate the volume of gas that is being produced at the electrode. For example, let's take a question, right? Let's go ahead and take a possible question. Let's see. Okay. They say calculate the mass deposited at the cathode during electrolysis when current of, let's take 1.5 amperes flows through molten lead to bromide for 20 minutes. Okay. So what we are going to go ahead and do is that we have to calculate what is the mass of a deposit at the cathode. First thing is first, let's figure out what is going to the cathode and what is going to the anode. We have in our question molten lead bromide, Pb2Br. You and I know that since this is molten, so there are only two ions, lead ion and bromide ion. Lead ion will go to the cathode because it's a cation, and bromide ion will go to the anode because it's an anion. Bromide ion will undergo, the lead ion will undergo reduction and the bromide ion will undergo oxidation. So over here, my Pb2 plus 2E gives me Pb. So I always first want to make my overall equation or my half ionic equation actually, because I want to go ahead and determine what is the mass of electrons that is actually involved in this particular situation, right? So there are 2 moles of electrons. You and I can clearly see that there are 2 moles of electrons that are actually involved in this particular situation. So now let's go ahead and actually do our calculation. So we have to find out how much charge do I need, right? So I have 2 moles of electron. What did I tell you? 1 Faraday is the amount of charge I need for 1 mole of electron. So over here, I have 2 moles of electrons, which means that I need a charge of around 2 Faraday, right? 2 Faraday, if I want to calculate 2 Faraday, so 1 Faraday is 96,500. And if I multiply it by 2, that will give me the value for 2 Faraday. So I get 193,000 coulombs. Okay. Now that I have the value for my charge, I can now go back to the formula that I studied. Charge is equals to current into time. How much current am I using? 1.5. How much time am I using? I'm using 20 minutes, but I will have to multiply it by 60 to turn it into seconds. So I will end up getting my answer as 1800 coulombs. Now, 1800 coulombs is the charge that I am providing. How much charge do I need per mole? 190,000. This is the value for 1. This is the total charge I am actually providing to the circuit. So for 1 mole, I need 100 and, or I'm saying 1 mole of lead. Okay, not 1 mole of electron, 1 mole of lead. For 1 mole of lead, I need this much charge. So how many moles will I be able to produce if my charge is 1800? Cross multiply. So I will get 1800 is equals to 193,000 x. 1800 upon 193,000 is equals to x. X is going to come out as, hold on 1 second. 1800 divided by 193,000, 0.0093. So these are the moles of lead I will be able to produce by using 1.5 ampere current for 20 minutes. So step number 1 was to calculate how much charge do I need, right? Calculate how much charge needed per mole. So for 1 mole, how much charge do I need? Step number 2, calculate how much charge provided. How much charge is actually coming from my power supply? How much charge is being provided by my power supply? Then step number 3, I will calculate the number of moles. So for 1 mole, I need this much charge. My circuit is giving me 1800 coulombs of charge. So then I will calculate the number of moles. How many moles will I be able to produce if I'm using 1800 coulombs of charge? I get my answer as 0.0093. Part 4, they are saying in the question, calculate the mass deposited. So we know moles is equals to mass over mR. Our moles are 0.0093. mR of this is 207. So I multiply by 207. I will get my answer as 1.93. So the mass of lead that I will be produced or that I will be able to deposit on the cathode is going to be 1.93 grams. And that's how I'm getting my answer. Clear? Making sense?
Yes. Mass of only lead?
Yes,
One.
because they're asking us at the cathode. So since
Okay.
they said at the cathode, we only have to worry about the lead. We don't have to worry about bromide.
Right. Okay.
So I told you we can use this concept to calculate the mass as well as the volume. So how will we calculate our volume? Let's take a look at that as well. Okay, let's say we are calculate the volume of oxygen is easy, of oxygen at RTP when concentrated aqueous solution of sulfuric acid is electrolyzed using a current of 0.5 amperes. Right? So again, first thing is first, let's take a look at our solution. The first thing we have to do is figure out our electrolysis because I need my half equation. Without the half equation, I cannot solve the question. So this is concentrated. This they said is concentrated aqueous solution of sulfuric acid. Sulfuric acid is H2SO4. Since this is aqueous solution, so it will have hydrogen ion and hydroxide ions from the water, from the aqueous component, and then of course hydrogen ion and the sulfate ions. So between these two hydrogen ions, we don't have much of a choice. The only ion that will go to the cathode is the hydrogen ion. Over there, it will get reduced, and this will be the equation. Over here, I have a choice between hydroxide and sulfate, right? So between between your hydroxide and sulfate, right? In IGCSE, we used to look at the reactivity series to decide who will go to the cathode and who will go to the anode. Now you will actually see that we do not look at reactivity series, we look at something we call electrode potential. I will tell you about that in a bit. So between hydroxide and between sulfate, if you look at electrode potential, or even if you look at the reactivity series, hydroxide ion is much easier for hydroxide ion to go to the anode compared to the sulfate ion. So the hydroxide ion will go to the anode. When the hydroxide ion will go to the anode, it will give us water, oxygen gas, and of course electrons. I'm writing on this side because we always show electrons with a positive side. I will balance it. So I have I put a 2 over here, then I put a 4 over here and 4 over here. So I'm getting 4 moles of electrons. This is why we're making equations, so we can actually putting in the effort of figuring out the electrolysis, so we can make our equations. Now, after that, 1 mole again is equals to 1 Faraday. 4 mole is equal to 4 Faraday. So 4 Faraday is equals to 96,500 multiplied by 4. That gives me the answer of 386,000 coulomb per mole. Step number 1 was to calculate how much charge is required. Step number 2 is to calculate how much charge am I giving, right? Okay, I did not tell you the time, so let me just add the time in it. Let's take, let's say 30 minutes, okay? Let's say 30 minutes. So again, I'm going to do Q is equals to ID. My current is 0.5, my time is 30, and I'll multiply it by 60 because, of course, I'm calculating it per second. So I will end up getting 900 coulombs as the charge that I have. So the charge that I need for one molecule of oxygen or 1 mole of oxygen, the charge I need for 1 mole of oxygen is 386,000. The charge that I have is 900 coulombs. So how much moles will I be able to produce? 900 divided by 386,000. That will give me my number of moles as 900 divided by 386,000. That will give me the answer of 0.00233 moles. Step number 4, I know my formula. Moles is equals to volume over 24 dm cube. This is why I specified RT. Okay, 24 dm cube is the value at room temperature pressure. Keep it in mind that if we have a different temperature or the pressure is different, then we cannot use 24 dm because 24 dm cube is the volume for 1 mole of gas at room temperature. If I change that room temperature, if I change the pressure, then the volume of 1 mole of gas automatically changes. So in that case, if they do give you a situation like that, then they will tell you what is the molar volume. They will tell you that. So our mole is 0.00233 0.00233. I multiply it by 24 to get my volume. So I get my final answer as 0.0559. So I'll just round it off to 0.056. And that's how I put my calculation. So this is how you can calculate what is the volume and what is the mass of any substance being produced. But yes, for all of this, you will first have to solve your electrolysis. So you can make your half equation. So you know who needs to go to the cathode and who needs to go to the anode. Okay. We can also calculate the Avogadro constant, by the way, by using electrolysis, right? So we can calculate the Avogadro constant simply by, taking the charge on one mole of electrons, right? If I take the charge on one mole of electrons and I divide it by the charge on one electron. So the charge on one mole of electron, that's 1 Faraday or 96,500. And I divide it by the charge on one electron, that is 1.6 into 10 raised to power negative 19. So we can actually use this to calculate the Avogadro's constant as well. Okay, other than this, okay. Now, this was a bit of something that we had studied and we had gone over our calculations. Now, let's go over a concept that we most definitely have not gone over before. And that is the concept of electrode potential. When we talk about electrode potential, so a redox equilibrium can exist between two chemically related species that are in different oxidation states. Let me give you an example. Let's say I have copper. This copper gains 2 electrons to become copper metal. This copper metal can lose 2 electrons to become copper ion. So this is a redox reaction. It's in the form of an equilibrium. So we say redox equilibrium. These two species are chemically related to each other. They're both copper, but they're both in different oxidation states. So a redox equilibrium can exist between two chemically related species that are in different oxidation state, right? Now, let's say, let's take the example of copper. I have a copper rod and I have placed it in a solution of, let's say, copper sulfate. Okay. I have taken my copper rod and I have placed it in a solution of copper sulfate. So the copper sulfate solution has copper ions in it, and this rod is made up of copper metal. Now, what is going to happen? Metal atoms from the rod entering the solution as metal ions. So the copper atoms in the rod, this is the rod. So the copper atoms in the rod will entering the solution, they will be entering into the solution in the form of copper ions, right? So as a result, what will happen? Since I am taking my copper atom and I'm turning it into a positive ion, so what happens? Electrons are getting lost somewhere. Right? Because I have my copper metal, I have my copper rod. The copper rod is made up of copper atoms. When my copper atoms will turn into copper ions, they will lose electrons, reduction. Those electrons will be left behind on the surface of this copper rod. Now, what will happen? The ions in the solution, the ions in the solution, because I told you that the solution will have ions inside of it. It's made up of copper sulfate. So the ions in the solution will accept electrons from the metal rod, because the metal rod has electrons in it because of reduction of copper. They have electrons in it. So the ions in the solution will be able to accept electrons and turn back into copper metal. So as a result, eventually you will end up getting to a equilibrium stage where you will have a redox equilibrium, when the rate of electron gain equals the rate of electron loss. So the amount of electrons being gained by copper ion is equal to the amount of electrons being lost from the copper atom as it dissolves into the solution, right?
Yes.
So uh, so now, what if I take my copper and I compare it to other metals? So, copper is pretty low in the reactivity series. What if I take a more reactive metal and I set up a similar equilibrium and I compare the two of them? So, you will see that the equilibrium for copper is actually lying towards the right side, meaning that it's lying towards the copper atom, meaning that it's lying towards the forward reaction, right? It's lying towards the forward reaction. So let's say I'm comparing iron and copper. So the equilibrium for copper is going to be more towards the right side. The equilibrium for iron is going to be comparatively, in comparison, more towards the left side, more towards the reactant side, right? This is why copper ions are relatively easier to reduce. So if you have a solution where you have iron and copper, so who will get reduced at your cathode? Copper. So far we had studied in IGCSE, all we had studied was, oh, copper is less reactive, so copper will go to the lower in the reactivity series, so copper will go to the cathode. Now we can understand the why behind it, right? The why behind it is because of this redox equilibrium. So iron will have an equilibrium, copper will have an equilibrium, but since copper is, the equilibrium for copper is more towards the right side compared to iron. As a result, it's easier for copper to get reduced compared to iron. Hence, copper is going to gain electrons much more easily compared to iron, because the forward reaction for copper is going to happen much easier compared to the forward reaction for iron. That's why your copper is going to get preferentially deposited at the cathode, right?
Yes.
So the position of equilibrium will differ for different combination of metals placed in a solution of their ions. So if I take copper and copper sulfate, I'll get different result. If I take zinc and zinc sulfate, I will get different results. If I take iron and iron sulfate, I will get different results, right? So when I take a metal and I put it into a solution of its ions, an electrical voltage is established between the metal and the metal ions. So uh, we can measure this difference. We can measure the difference in the potential between the metal and the metal ion system, and I can compare it to another system that is known as electrode potential. So if I take my zinc and I place it in a zinc solution, and I take copper and I take a look at copper solution, and I compare the voltage, I cannot actually measure the voltage directly, but I can take two different systems. One system is zinc and zinc sulfate. The other one is copper and copper sulfate. So I can take those two and I can measure the difference in voltage between the two systems. That difference in voltage is what I will call as electrode potential, right? And what do we normally compare it with? So the values that are given in your data booklet, they are all in comparison to hydrogen. Okay, all of them are in comparison to hydrogen. So we have set up a system, zinc and zinc sulfate, for example, hydrogen and a solution of hydrogen ions, for example, acid, whatever. So I have set up two systems, the metal or the atom and the ions, and the atom and the ions. and then I'm comparing the difference. So electrode potential is, how am I getting it? I am basically measuring the difference in potential, or in terms of voltage, between a metal and a metal ion system compared to another system. So we generally compare it to hydrogen. That's the one that we normally compare it to. We generally compare it to hydrogen. Those are the standard electrode potentials that you will find in your data booklet. So the values you see in your data booklet, the values we are going to use for our solving our past paper questions, they are all in comparison to hydrogen. Now, so okay. So so far it's making sense, right? So far we don't have any confusion.
No.
Okay, all right. So this is what electrode potential is, right? So when you talk about it by convention, by tradition, when I talk about electrode potential, I'm talking about a reduction reaction, right? Now, for example, let's say that I have something like this. I have aluminium. So aluminium ion will gain 3 electrons to become aluminium metal. And this is my redox equilibrium. The more positive or less negative, whatever term you like to use, the more positive your electrode potential, the easier it is to reduce the ions on the left side, right? Meaning that if, for example, if I take silver, silver has a more positive value. So it's more easier for me to reduce silver as compared to aluminium. On the other hand, let's take zinc. Zinc, on the other hand, has a more negative or less positive electrode potential. So it's harder to reduce the ions for zinc compared to silver. So easier for me to, so this is how you're going to decide which one, when you're going to take a look at your data booklet, how will you decide which one is easier to reduce, right? So you will decide it based on the value of electric potential. The more positive the value of electrode potential, the easier it is going to be for you to go ahead and actually, uh, reduce that particular ion. Now, when let's talk about how we can now measure. So we have talked about what electrode potential is, but how can we measure standard electrode potential? Just give me 1 second. Sorry, I just need to grab a tissue. Just 1 second. Okay. So, when we talk about measuring the standard electrode potential, so, okay, we have to talk about what is a half cell. Okay. So a half cell is what I just explained to you. If I take copper and I put it in a solution of copper ions, that is known as a half cell. Now, what we can do is that we can, uh, I can take two half cell and I can combine them together to make an electrochemical cell. Let's talk about it. How we can do it. I have a half cell. A half cell would be, for example, I take a pure copper rod and I place it into a solution of copper ions. This system, this, metal ion system is known as half cell. Now, we're of course going to do this under standard conditions. What are the standard conditions? The concentration of our copper solution is going to be 1 mole per dm cube per dm, right? Of course, and we have to make sure that our temperature is room temperature, so around 25 degrees centigrade or 298 kelvins, and that we are going to use pure copper rod. These are the standard conditions that we have to ensure are present. Now, if I connect two half cells together, if I connect two half cells, I can make a type of a cell we call electrochemical cell. Okay. Then I can measure the voltage between these two half cells, right? So we can now, how can I connect these half cells together with each other? Okay. Half cells can be connected with each other either using wires, right? Connecting the metal rods to a high resistance voltmeter. That's one thing I can do. So if I draw this for you, let's say this is one half cell where I have copper and I have a solution of copper ions. And this is another half cell that I have where I have zinc and I have a solution of zinc. So what I can do is that I can connect the metal rods to a high resistance voltmeter, basically to a voltmeter, right? The electrons will flow around this external circuit from the metal with more negative electrode potential. So if zinc is the one that has more negative electrode potential, the electron will flow from the one that is more negative towards the one that is more positive, right? So the electrons will flow from the one that is more negative towards the one that is going to be more positive. This is one way that you can do it. The second way you can join the two half cells together is by using something known as a salt bridge, right? A salt bridge is basically made from a filter paper, right? And we soak it in a solution of potassium nitrate. So I can take the filter paper, I can soak it in potassium nitrate, and I put that between the two cells. Okay, we call it a salt bridge. So I can either do that. Those are the two options that I have. So this is my salt rich. Potassium nitrate, filter paper soaked in potassium nitrate. So what's going to happen? This is going to allow the movement of ions between the two half cells so that the ionic balance is maintained, right? The salt bridge does not allow the movement of electrons. The electrons will move from the voltmeter, from the wires that are connected to the voltmeter. That is where the electrons will move from. But if I don't place the salt bridge, eventually my ions will no longer be balanced with each other. And that will affect my result. So the salt bridge allows the flow of ions to make sure that the ionic balance is maintained. The electrons will flow through the wires and the voltmeter. Now, what is going to happen? We have copper and we have zinc. So copper, if you take a look at the equation for copper, this is the equation for copper. And hold on, we have data booklet, right? Yeah. So the electrode potential for copper is plus 0.34. Then we have zinc. The electrode potential for zinc is minus 0.76. So clearly you can see zinc is the one that is more negative and copper is the one that is more positive. What does that tell us? That tells us that it is easier to reduce copper as compared to zinc. Zinc ions are more difficult to reduce compared to copper ions, right? So what is going to end up happening? That the zinc is going to so the zinc electrons will flow from zinc to copper, right?
Yes.
So who can get reduced more easily? Copper gets reduced more easily. So the copper metal is going to turn into copper ions. Over here, the copper metal will turn into copper ions. As a result, electrons will start to accumulate on top of the copper, right? Those electrons will then those electrons will then so hold on 1 second, just give me 1 second. Okay, so it is much easier for copper to be reduced compared to zinc, right? So what's going to happen? That means zinc is going to get oxidized. Okay, zinc is the one that's going to get oxidized and the copper is the one that's going to get reduced. So your zinc is going to get oxidized where it will lose electrons and turn into zinc ion. In the process, the electrons will accumulate on the zinc rod. These electrons will travel from the zinc to the copper rod. Now, over here, the electrons will accumulate on the copper rod. Copper reduces much more easily because its electrode potential is positive. So copper will gain electrons and it will turn into copper 2. So it will actually, the copper 2 plus ions will turn into copper metal, right? And this flow of electrons is going to make sure that our that our cell is going to be working, that our electrochemical cell is going to be working. So and in this particular case, this will be positive and this will be negative, right? The terminal from where electrons flow, that's the negative one. But what is happening to zinc? Oxidation. And what is happening over here? Reduction. So when I'm going to name it, in this case, cathode is my positive one and anode is my negative one. So the positive cathode, remember that. Negative is not always anode. That's an electrolysis. This is not electrolysis, this is a cell where I'm making electricity. I'm not using electricity. So electrolysis and cell are opposite to each other in this way. In a cell, the anode is negative and cathode is positive. In electrolysis, it's the other way around. The cathode is negative and the anode is positive. But what is fixed? Reduction and oxidation. Reduction is always at cathode, oxidation is always at anode. And that's what you can see happening over here as well, right? So over here, zinc is the negative electrode because the electrons are flowing from zinc towards copper, right? But at the same time, what is happening that over here, my copper ion, because copper has a higher electrode potential, it will get reduced more easily. So it will get reduced more easily. So reduction is happening over here. Now, this becomes the positive electrode, but since reduction is fixed, reduction always happens at cathode. So my positive electrode will be the cathode and my negative electrode will be the anode. So positive and negative is not fixed, but reduction and oxidation is fixed, right? Similarly, so this is basically how I can take two half cells and I can connect them together to measure my make an electrochemical cell. And now we were talking about how we can measure our standard electrode potential. We can measure standard electrode potential in three combinations. Either we can take a so one is fixed, that we have a hydrogen electrode that is fixed. I told you all our data book readings are with the hydrogen electrode. We can either have that, and the other possibilities we can have metal and a metal ion half cell like this. The second possibility is we can have a non-metal and a non-metal ion. So chloride and so chlorine and chloride ion, iodide and iodide ion. The third possibility is we can have the ion and the ion half cell, right? That's the third possibility. So these are the three types of systems that we can go ahead and use to actually measure our standard electrode potential. So I think, okay, Anusha, I think we'll go ahead and stop it over here for today. We have to go ahead and discuss how we can measure our standard electrode potential, and we have to talk about how we can use our standard electron potential to figure out what will be the direction of the electron flow, how will we predict if the reaction is going to occur or not. And so all of this, inshallah, we'll go ahead and take a look at in the next class. All right.
Okay. Thank you.
Okay, thank you so much, Anusha. See you in the next class. Have a good day.
You too. Bye.
Allah Hafiz. Bye.